Since the dawn of the space age, Mars has stood as the ultimate frontier, a silent, frozen sentinel beckoning humanity to cross the cosmic void. But the Mars of today is a hostile wasteland, a world where the temperature averages -80 degrees Fahrenheit, and the atmosphere is a thin, toxic veil of carbon dioxide. To call this planet home, we must do more than just visit. We must fundamentally rewrite its planetary physics. This is the story of terraforming, the most ambitious engineering project ever conceived by the human mind. It is a process that would take centuries, requiring us to act as planetary architects, sculpting the climate, the chemistry, and the biology of an entire world. We are not merely talking about building pressurized domes. We are talking about unbinding the shackles of a dead planet and breathing life into its ancient dust. As we stand on the precipice of becoming a multi-planetary species, the question is no longer if we can reach Mars, but whether we have the collective will and technological prowess to transform its crimson deserts into verdant forests. This journey begins with understanding what Mars lost billions of years ago and how we might restore its long-lost habitability through the power of advanced science and sheer human ingenuity.
The primary obstacle to a green Mars is its atmosphere, or rather the lack thereof. Currently, the Martian atmospheric pressure is less than 1% of Earth's at sea level. If you were to step onto the Martian surface without a pressure suit, the liquid in your body would begin to boil at body temperature due to the Armstrong limit. This thin veil is composed of 95% carbon dioxide, which, while useful for plants, is far too sparse to trap heat or protect the surface from deadly solar radiation. To transform Mars, we must first thicken this atmosphere significantly. We need a Goldilocks pressure that allows liquid water to exist on the surface without instantly evaporating or freezing. Achieving even a third of Earth's pressure would be a monumental shift, creating enough resistance to allow for more efficient landing of heavy spacecraft and providing the thermal mass necessary to stabilize the planet's erratic temperature swings. This atmospheric thickening is the foundation upon which all other terraforming efforts rest. Without a substantial gaseous envelope, any warmth we generate will simply escape into the vacuum of space, leaving the planet as cold and lifeless as it has been for the last 3 billion years. We must find a way to trap gas, and to do that, we need to look at the hidden reservoirs of volatiles locked within the Martian crust and polar caps.
One might wonder why Mars lost its atmosphere in the first place. The answer lies deep beneath the surface. Unlike Earth, Mars lacks a functioning geodynamo, a molten, rotating iron core that generates a global magnetic field. Without this protective magnetosphere, Mars is defenseless against the solar wind, a stream of high-energy particles from the sun that relentlessly strips away atmospheric gases. Over eons, this process turned a once wet and warm Mars into the desiccated husk we see today. If we were to thicken the atmosphere today without addressing this underlying issue, the sun would simply blow it all away again. Therefore, a critical step in the terraforming blueprint involves creating an artificial magnetic shield. One radical proposal involves placing a powerful superconducting magnet at the L1 Lagrange point between Mars and the Sun. This would create a magnetic dipole that sits in front of the planet, deflecting the solar wind and creating a protected plasma tail in which Mars can safely reside. While this sounds like the stuff of science fiction, the physics are sound. By shielding the planet from the solar wind, we allow the natural outgassing of the planet to rebuild the atmosphere over time, and more importantly, we protect any future biological life from the searing effects of cosmic radiation that currently sterilizes the Martian surface.
To jumpstart the warming process, we need to harness the power of the sun. Mars receives less than half the solar energy that Earth does, making it a deep freezer of a world. One of the most discussed methods to rectify this is the use of orbital mirrors. Imagine vast sheets of aluminized mylar, spanning kilometers in diameter, positioned in high Martian orbit. These mirrors would act as massive magnifying glasses, reflecting sunlight onto the frozen carbon dioxide and water ice at the Martian poles. As the poles sublimate, turning from solid ice directly into gas, they would release vast quantities of CO2 into the atmosphere. This creates a feedback loop. More CO2 leads to a stronger greenhouse effect, which raises the temperature, which in turn melts more ice. This runaway greenhouse effect is exactly what we want to trigger on Mars. The beauty of this approach is its relative simplicity in terms of physics, even if the engineering of such large structures in space remains a colossal challenge. By targeting the poles, we tap into a natural battery of stored gases that has been locked away for millions of years. Once the temperature at the equator stays above freezing for a significant portion of the year, we begin to see the first signs of a world capable of supporting liquid water, the essential precursor to any green transformation.
While CO2 is a decent greenhouse gas, it is not particularly efficient on its own. To really turn up the planetary thermostat, we might need to resort to the production of super greenhouse gases. On Earth, we view perfluorocarbons, or PFCs, as environmental pollutants, but on Mars, they are exactly what the doctor ordered. These synthetic gases are thousands of times more effective at trapping heat than carbon dioxide, and they do not deplete the ozone layer or pose a toxicity risk to future inhabitants. We could deploy automated factories across the Martian surface specifically designed to manufacture these gases from the fluorine and carbon already present in Martian soil. By pumping these gases into the atmosphere, we could accelerate the warming process by decades or even centuries. This is an example of purposeful climate engineering. The goal is to create a blanket for the planet that prevents infrared radiation from escaping back into space. As the planet warms, the frozen water ice beneath the surface, or regolith, would begin to liquefy, creating a subterranean plumbing system that could eventually feed rivers and lakes. This phase of the project requires a massive industrial infrastructure, but it represents the first true pulse of a living planet as we actively manipulate the global chemistry to suit the needs of biological life.
As the temperature rises, the most magical transformation of all begins to occur: the return of liquid water. Evidence from rovers and orbiters tells us that Mars was once a world of roaring rivers and vast northern oceans. That water didn't all vanish into space. Much of it is still there, locked in the soil and the polar caps as permafrost. As our warming efforts take hold, we would see the first Martian spring in billions of years. Initially, this water would be highly saline, a briny sludge that emerges from the slopes of craters. But as the atmospheric pressure increases, this water would stabilize. We would see the formation of lakes in deep basins like Hellas Planitia, where the pressure is highest. This is a critical milestone. Liquid water is not only necessary for life, but it also helps to regulate the climate and distribute heat across the planet. The presence of surface water would change the very color of the planet, from a dusty red to a darker, more varied palette of blues and browns. However, this water would initially be toxic to Earth life, filled with perchlorates, salts that are hazardous to humans. The next stage of our journey involves cleaning this water and the soil to prepare for the first biological pioneers. The green in Green Mars starts with the chemistry of the water and the readiness of the Martian Earth to support its first inhabitants.
No amount of mechanical engineering can match the transformative power of biology. Once the environment has been stabilized with sufficient pressure and warmth, we would introduce the first pioneer species. These wouldn't be trees or flowers, but extremophiles, organisms like cyanobacteria, lichens, and certain types of algae that can survive in the harshest conditions on Earth. These biological engines would be genetically engineered specifically for Mars, designed to thrive in high CO2 environments and withstand higher levels of UV radiation. Their job is twofold. First, they would begin the slow process of photosynthesis, converting the abundant carbon dioxide into oxygen. Second, they would begin to break down the Martian regolith, turning sterile dust into actual soil by adding organic matter. This is the slow, grinding work of terraforming. It might take centuries for these microorganisms to make a measurable dent in the oxygen levels, but they are the foundation of the Martian biosphere. Imagine vast carpets of black and green lichens spreading across the rocks of Olympus Mons, slowly softening the jagged landscape and preparing it for more complex life. These tiny organisms are the unsung heroes of planetary transformation, working 24 hours a day to build a world they will never truly see. They are the bridge between a dead rock and a living garden.
Oxygen is the holy grail of terraforming, but it is also one of the hardest gases to accumulate in large quantities. To create an atmosphere that humans can breathe without respirators, we need to reach an oxygen level of at least 13 to 15%. However, a pure oxygen atmosphere would be a fire hazard of catastrophic proportions. We need a buffer gas, and on Earth, that gas is nitrogen. Nitrogen makes up 78% of our air and is vital for plant growth. Mars, unfortunately, seems to be nitrogen poor. Finding enough nitrogen to thicken the atmosphere and support a full biosphere is one of the greatest challenges in the terraforming timeline. We might need to import nitrogen by redirecting ammonia-rich asteroids from the outer solar system to impact the Martian surface or burn up in the atmosphere. This sounds extreme, but terraforming is a project of astronomical scales. Each impact would deliver millions of tons of nitrogen and water vapor, further warming the planet. Over centuries, the combined efforts of biological photosynthesis and nitrogen importation would slowly shift the atmospheric composition. The sky would begin to change from its iconic salmon pink to a pale, hazy blue, as the thicker air begins to scatter sunlight in a process known as Rayleigh scattering, the same phenomenon that gives Earth its blue sky.
Before we can plant our first forests, we must deal with the poison in the soil. Martian regolith is laced with perchlorates, which are toxic to most Earth-based life forms and would prevent the growth of traditional crops. Cleaning an entire planet's soil is a daunting task, but it could be achieved through a combination of chemical washing and bioremediation. We could deploy specialized bacteria that actually eat perchlorates, converting them into harmless chlorides and oxygen. This would be done in localized areas first, valleys and craters that are slated to become the first agricultural zones. As these bacteria do their work, they also enrich the soil with nitrates, the very fertilizer that plants crave. We would see the first Martian farms not in open air, but in massive, unpressurized greenhouses that utilize natural sunlight while shielding plants from the harshest elements. These greenhouses would serve as the nurseries for a new Martian ecology. The goal is to create a self-sustaining cycle where the soil provides nutrients, the plants provide oxygen, and the atmosphere provides protection. This stage marks the transition from planetary engineering to planetary gardening, where human intervention becomes more about nurturing growth than forcing change through brute force physics and industrial chemicals.
As the soil is cured and the air thickens, the first visible greenery will emerge. This won't be the lush grass of a golf course, but rather a Martian tundra. Geneticists will have spent centuries preparing for this moment, designing plants that can survive the still chilly Martian nights and the lower light levels of the fourth planet. These Martian plants might have darker leaves to absorb more sunlight, or thick waxy coatings to prevent moisture loss. We would see mosses, ferns, and hardy shrubs beginning to take hold in the sheltered lowlands. This is a pivotal psychological moment for the human inhabitants of Mars. For the first time, the view outside their windows isn't just shades of red and orange, but the vibrant, hopeful hue of green. These plants would begin to create a local water cycle, transpiring moisture into the air and contributing to the formation of the first Martian clouds. We would see the first Martian rain, not the acidic downpours of the early terraforming stages, but gentle showers that sustain the spreading carpet of life. The planet is no longer just a place where we survive. It is becoming a place where life, in its own alien way, is beginning to thrive and claim the land for its own.
With the success of the tundra ecosystems, we can finally look toward the ultimate symbol of a green planet, the forest. Trees are the ultimate carbon sequesters and oxygen producers, but they require a stable climate and a reliable source of water. In the deep canyons of Valles Marineris, where the air pressure is at its highest and the walls provide protection from the wind, we would plant the first Martian forests. These trees would likely be genetically modified versions of Earth's hardiest species, such as the bristlecone pine or the Siberian larch, but with adaptations for the 1/3 gravity of Mars. In lower gravity, trees could potentially grow much taller than they do on Earth, creating massive, towering cathedrals of wood and leaf that reach hundreds of feet into the thin Martian air. These forests would act as the planet's lungs, pumping out oxygen and stabilizing the soil on a global scale. As these forests spread,
They would change the planet's albedo, the amount of sunlight it reflects, further warming the world. The sound of wind rustling through Martian leaves would be the anthem of a successful terraforming project, a sound that hadn't been heard on this world in billions of years. The red planet is now truly beginning its transformation into the green planet.
As the biological engines of Mars accelerate, the planetary hydrology follows suit. The northern lowlands, once a vast, dusty plain, would slowly fill with water, becoming the Oceanus Borealis. This new ocean would cover roughly a third of the planet, providing a massive heat sink that further stabilizes the global climate. Rivers would carve new paths through the ancient craters, and the water cycle would become fully established. Snow would fall on the peaks of the Tharsis volcanoes, and seasonal rains would turn the once dead plains of Elysium into flowering meadows. This interconnected system of water and life is what we call a biosphere. At this stage, the terraforming process is no longer just a series of human projects. It is a self-sustaining biological machine. The planet has its own weather, its own seasons, and its own rhythms. The vast dust storms that once choked the planet would be suppressed by the moisture in the air and the root systems of the spreading vegetation. Mars is no longer a world of dust and rock. It is a world of water and life. While the air might still require an oxygen mask for humans, the environment is now hospitable enough for many types of Earth animals to be introduced, creating a complex food web that mimics the diversity of our home world.
The ultimate goal of terraforming is the open air stage. This is the point where the atmospheric pressure and temperature are high enough that humans no longer need pressurized suits to survive outside. You could walk across the Martian surface in ordinary clothes, perhaps with only a small oxygen mask, a rebreather, to supplement the still thin air. Imagine standing on the shore of a Martian sea, feeling the cool breeze on your face and watching the sunset, not as a tiny blue dot, but as a familiar golden orb through the hazy blue atmosphere. The psychological impact of this cannot be overstated. Mars would no longer be a colony or a base, it would be a home. Children would be born who have never known the inside of a pressurized dome, who see the green fields of Mars as their natural heritage. This stage of terraforming is the culmination of hundreds of years of effort, a testament to the idea that humanity can be a force for life in the universe. We would have taken a dead world and given it a second chance, creating a backup for Earth and a laboratory for the future of our species. The green Mars is no longer a dream. It is a physical reality that can be seen from space, a vibrant emerald jewel hanging in the blackness of the solar system.
The timeline for this transformation is measured not in years, but in generations. Current scientific estimates suggest that thickening the atmosphere enough to allow for liquid water could take 100 to 200 years. Creating a breathable, oxygen-rich atmosphere, however, is a much longer process, potentially taking upwards of 1,000 years or more using biological methods alone. This requires a level of political and social stability that humanity has rarely demonstrated. It requires a cathedral-building mindset, where the people who start the project know they will never see its completion. They are working for their great-great-grandchildren. This intergenerational contract is the heart of terraforming. It challenges us to think beyond our own lifespans and to consider the long-term future of our species. We must also consider the technological evolution that will happen during this time. The methods we use in the year 2100 will likely be replaced by far more efficient technologies in the year 2300. Perhaps nanobots will be used to disassemble rocks and release oxygen, or fusion-powered atmospheric processors will replace the need for orbital mirrors. The journey to a green Mars is a marathon, not a sprint, and every step forward is a victory for the preservation of life in the cosmos.
As we discuss the how of terraforming, we must also grapple with the why and the should. There is a significant ethical debate surrounding the transformation of Mars. Some argue that Mars has intrinsic value as a pristine wilderness and that we have no right to alter its natural state.
This planetary protection philosophy suggests that if there is even a microscopic chance that indigenous Martian life exists, perhaps deep underground, we must leave the planet alone. Others argue that the expansion of life is a moral imperative. By making Mars green, we are increasing the total amount of life in the universe and ensuring that the light of consciousness doesn't blink out if a catastrophe strikes Earth. Is terraforming an act of supreme arrogance, or is it our destiny as a tool using exploratory species? These questions will likely be debated for as long as the terraforming process itself lasts. As we begin to move the first stones and plant the first seeds, we must do so with a sense of humility and responsibility. We are not just masters of the planet, we are its stewards. The transformation of Mars is as much a test of our character as it is a test of our technology.
The logistics of terraforming are as staggering as the physics. To move the millions of tons of equipment, gases, and biological matter required, we would need a transportation infrastructure far beyond anything we currently possess. Space elevators, powered by carbon nanotubes, could provide a low-cost way to move materials from the Martian surface to orbit and back. Massive cycler ships would move between Earth and Mars like a cosmic conveyor belt, bringing the resources of the homeworld to the new frontier. This effort would likely be the focus of the entire global economy of Earth, a unified project that brings nations together in a common cause. The sheer scale of the labor involved would necessitate a new era of automation and robotics. Millions of autonomous drones would be responsible for planting forests, monitoring atmospheric changes, and maintaining the magnetic shield. The economy of Mars would evolve from one of survival and extraction to one of growth and sustainability. It is a vision of a future where humanity has moved beyond its planetary cradle and is actively shaping the solar system to be a more vibrant and hospitable place for all forms of life.
What will life be like for the first true Martians? On a green Mars, the low gravity would mean that every human is a natural athlete. You could jump 3 times as high and run with a lightness that Earth dwellers could only dream of. The architecture would reflect this, with towering, airy structures that would be impossible under Earth's heavy pull. Martian culture would likely be deeply rooted in an appreciation for nature, born from the knowledge of how much effort it took to create every blade of grass and every breath of air. The holidays on Mars might celebrate the arrival of the first rains or the planting of a new forest. The relationship between humans and their environment would be one of profound connection, as they live within a biosphere that is, in a very real sense, a product of their own ancestors' making. This new humanity would be different from the old, perhaps taller, with different bone structures, but still carrying the same curiosity and drive that led their forebears to cross the stars. Mars wouldn't just be a new Earth, it would be its own unique world, with its own history, its own beauty, and its own future.
The long-term stability of a green Mars is another critical consideration. Terraforming is not a one-and-done project. Even with a magnetic shield, the atmosphere would still require constant monitoring and maintenance. We would be, in effect, the life support system for an entire planet. This requires a level of technological longevity that we have not yet achieved on Earth. We must build systems that can last for thousands of years, outlasting the civilizations that created them. This constant fine-tuning of the climate would become a part of the Martian way of life. If the oxygen levels dip, more forests are planted. If the temperature falls, more greenhouse gases are released. This level of control could lead to a perfect climate, free from the natural disasters and instabilities that plague Earth. We could design Mars to be a paradise, optimized for the health and happiness of all its inhabitants. But this also places a heavy burden on future generations. They must remain vigilant, for if the machines stop and the forests fail, Mars will slowly but surely begin its slide back into the cold, red silence of the past. The price of a green planet is eternal stewardship.
As we look at the final stages of the greening of Mars, we see a world that is a testament to the power of life. The red planet has been reborn. The dust storms are gone, replaced by weather patterns that sustain a global ecosystem. The oceans are teeming with engineered plankton and fish,
and the forests are home to birds and insects brought from Earth. This is the ultimate insurance policy for our species, but it is also something more. It is an expansion of the sphere of life, the thin layer of the universe where life exists and thrives. By terraforming Mars, we are making the universe a little less lonely and a little more green. We are proving that we are not just a destructive force, but a creative one, capable of bringing life to the lifeless and warmth to the cold. The lessons we learn on Mars about climate management and ecosystem balance will undoubtedly help us better protect and restore our home planet, Earth. In the end, the project of terraforming Mars is as much about saving our first home as it is about building a second one. It is a journey of discovery that begins with a single step onto the red dust and ends with a walk through a Martian forest.
The transformation of Mars into a green planet is perhaps the most difficult challenge we will ever face, but it is also the most rewarding. It represents the transition of humanity from a planetary species to a galactic one. It is a story of hope, science, and the stubborn refusal to accept that a world must remain dead. As we look up at the red dot in our night sky, we are not just looking at a planet. We are looking at a future where the desert blooms, where the oceans roar, and where the air is sweet with the scent of pine. This is the vision of Mars reborn. It will take the work of thousands of years and the hearts of millions of people. It is a dream that belongs to all of us, a dream that starts with the realization that we have the power to change worlds. As we conclude this journey into the engineering of a green Mars, let us remember that the greatest tool we have is not our rockets or our robots, but our imagination. For if we can imagine a green Mars, we are already halfway to building it. The red planet is waiting. It is time for us to bring it back to life. Thank you for joining us on this deep dive into the future of our solar system. The journey is just beginning.